Hi students, the topic of this video is mechanical energy. First, let's define the energy. It's the ability to do work. The mechanical energy is the sum of the potential and the kinetic energy of an object. Let's remember the work. We have said that if an object displaces in the direction of force applied, then the work done is equal to force times the distance. So if a force does a work, then there's a change in energy. So work is the change in mechanical energy. So this is important. If there's a work done, then there's a change in mechanical energy. First, let's define the kinetic energy. It is the energy of motion. If an object has motion, it may be vertical or horizontal, then it has kinetic energy. There are many forms of kinetic energy. One, vibrational kinetic energy, is the energy due to vibrational motion. It means back and forth motion. Rotational kinetic energy, the energy due to rotational motion or circular motion. Here, a man is turning a merry-go-round, so this type of motion is rotation, and we are concerned with rotational kinetic energy. And the translational kinetic energy, it is the energy due to motion from one location to another. So this car is making a translational kinetic energy. An object may have more than one type of kinetic energy. For example, a rolling ball, it has both translation kinetic energy and a rotational kinetic energy. This year we are going to cover just the translational kinetic energy. The kinetic energy of an object arises from the net work done on it. So the work done by the force at a distance x is equal to F times x. And it is seen that here the object has no velocity, so zero kinetic energy. But at the end of the distance x, it has a velocity, so it has a kinetic energy here. So there is a change in kinetic energy, and this arises from the work done by the force. So the formula for this kinetic energy gained by the object is calculated by the formula 1/2 mass times the velocity square. M is the mass, it is taken in kilogram. V is the velocity, it is taken in meter per second, and this is the kinetic energy in the unit of joule. Let's do an example. What's the kinetic energy of a sliding solid cylinder with a mass of 2 kg going with a speed of 20 meters per second? Its kinetic energy is equal to 1/2 mass times velocity square. So when we put the values, we have the kinetic energy equal to 400 joules. A box is pushed 10 meters across a floor in each case shown. All boxes have an initial velocity of 10 meters per second to the right. The mass and the net horizontal forces are given. Rank the change in kinetic energy of the boxes. The change in energy is equal to work done, and work is equal to force times the distance. So in A, the force is 75 and the distance the same, 10 meters. So the work done on A is equal to 75 times 10, 750 joules. In B, force the same, distance 10 meters. So it is also equal to the work done on B. In C, the force is 50 Newton, again displacement 10 meters. So the work done on C is equal to 50 times 10, 500 joules. And in D, the force 100 Newton, the distance 10 meters. So the work done on D is equal to 100 times 10, 1000 joule. So you see here that the work done on D is bigger, so its kinetic energy change is bigger than the A is equal to B, and it is greater than C. A constant 120 Newton force is applied on a 4 kilogram object which is initially at rest. What is the velocity of the object after it displaces 20 meters? So here I see that I have the force, I have the distance. So the work done is equal from force times distance, 160 times 20, 3,200 joules of work done. So this is equal to the change in kinetic energy. As it has no kinetic energy initially, so all work done is converted into kinetic energy at the end of 20 meters. So 3,200 joule is equal to 1 over 2 times mass times v square. So I have the velocity v square 1,600. So take the root and find the velocity as 4 meters per second. Force applied versus position graph of a 2 kilogram object which has an initial velocity of 5 meters per second is given, and the velocity of the object after 20 and 30 meters are asked. Now we know that the area under the force position graph gives me the work done. So for A, I'm going to find the area of this triangle. Here the work done is equal to, from the area of the triangle, 10 times 20 over 2, which is equal to 100 joule. So for A, the work done is equal to change in energy, which is equal to the final energy minus the initial energy. So 100 joules of work is done. Final energy from the formula of the kinetic energy, 1 over 2 times mass 2 times V final square minus 1 over 2 times mass 2, the initial velocity 5, so the square of 5, 25. So here I have V final square is equal to 125, so the final velocity is equal to 5 root 5 meter per second. Now for 30 meters, so I have to take the all area under the graph from 0 to 30 meters. So this area is already calculated as 100 joule. This area plus is equal to, from the area of the rectangle, 100 times 10 times 10, 100. So I have in total 200 joules of work done. So for B, again the work done is equal to the final kinetic energy minus the initial. So 200 is equal to 1 over 2 times mass 2 kilogram B final square minus 1 over 2 times 2 mass and the initial velocity 5 square. So here I have the V final square is equal to 225. So I have the final velocity equal to 15 meters per second. The second type of mechanical energy is the gravitational potential energy. Potential energy is the stored energy of position possessed by an object. There are many forms: the gravitational potential energy, the elastic potential energy, and electrical potential energy. Gravitational potential energy is the energy stored in an object as the result of its vertical position or height. The energy is stored as the result of the gravitational attraction of the Earth for the object. Let's see that we have an object with a mass of m and it has the gravitational force, the weight, equal to mg. In order to raise this object to a height of h, we have to apply minimum value of force which is equal to the weight of the object. So this force is applied in a vertical direction and the vertical displacement is equal to h. So from work done, force times the distance, force applied is equal to weight of the object and distance taken is h. So as work done is equal to change in energy, here the object gains potential energy. So the potential energy has the formula mgh. This is the formula we are going to use. Here m is the mass, always taken in kilogram. G, you know that gravitational acceleration, which we generally take as 10 meter per second square, and h is the height of the object taken in meter. So this is the potential energy which has the unit joule. A boy goes from the point O to K by using stairs and goes from K to L over an inclined plane. Compare the works done against gravity of these two motions. The work done against gravity means the change in potential energy, which is equal to mg times h. So when the object rises from the position O to K, you see that it has a vertical distance h. So at K, it has the potential energy which is equal to mgh. When it goes from K to L, it again displaces a vertical distance of h. So the potential energy gained from K to L is equal to again mgh. So this is the work done in going up the stairs and this is the work done going up the inclined plane. So you see that they are equal to each other, so I have the ratio 1. We've said that the potential energy is equal to m times g times the height. We think here the object as point object, but if the object is a rigid body, so how we're going to find the potential energy of a rigid body? We're going to take the center of mass of the rigid body. We're going to use the geometrical objects, and the geometrical midpoint of the object is the center of mass of the object. So it is the half the distance height, which is equal to 5 centimeter. So when I am calculating the potential energy at this position, again I have used the formula mgh. The mass is 2 kilogram, g 10, but here I'm going to take the height of the center of mass, which is equal to 5 times 10 to power minus 2 meter. So it has a potential energy of 1 joule. If it is upside down, so here my center of gravity will be here. This has a height of here 2 centimeters, so the height of center of mass is 1 centimeter. So at this position, the potential energy from the formula, I'm going to get mass times gravitational acceleration, the height of center of mass 10 times 10 to power 2 meter. So I have 0.2 joules of potential energy. The system given in the figures are made up of the identical cubes. So we are going to take the ratio of their potential energies. So let's say that every cube has a weight of P. They are identical. So in the figure 1, these two cubes has a center of mass here with a distance, let's say 1. So the total weight equal to 2p, and these two cubes has a center of mass here, so it has a height of 4 with a weight of 2p. So the total potential energy for the first figure is equal to 2p times 1 plus 2p times 4, which is equal to 10p. For the second one, take these two cubes, center of mass here with a distance 1 with a weight of 2p, and these two cubes, they have the center of mass here with a distance of 2, and in total has a weight of 2p. So when I calculate the total potential energy, 2p times 1 plus 2p times 2. So in total I have 6p potential energy. So when we take the ratio, I found the solution as 5/3. Compare the works done in each figure. There's no friction. We know that the work done is equal to change in potential energy. Initially, they have no potential energy. So the potential energy is equal to mg times h. Mg is equal to weight of the object. So weight times the height will give me the work done. So in figure 1, the weight p and the height h. So work done in figure 1 is equal to p times h into the height 2h. So the work done is equal to p times 2h, and in 3, the height of h, p times h. So you see that V2 is bigger than V1 is equal to V3. Another form of potential energy is the elastic potential energy. It's the potential energy stored as a result of deformation of an elastic object, such as stretching of a spring. It is equal to the work done to stretch the spring, which depends upon the spring constant K as well as the distance stretched. Elastic potential energy can be stored in any elastic objects, rubber bands, bungee cords, trampolines, springs, and a rod drawn into a ball, etc. So you see here that we have an uncompressed spring. There is no force. When the spring is compressed with a distance of x, you apply a force F, and the spring applies a reaction force F equal to your force but opposite in direction. Then here in the third figure, the spring is stretched with a distance of x, and again the spring applies a force equal to this force in the opposite direction. So force applied on the spring is equal to K, the spring constant, times the amount of deformation. So K is the spring constant, X is the amount of compression or stretch, and this is the force of spring. If this is the force of applied, then this is positive. If this is the force of spring, then it is negative, because the force applied by the spring is equal to the force applied but opposite in direction. According to Hooke's law, the force required to stretch the spring will be directly proportional to the amount of stretch. Since the force has the form F is equal to minus K times X, So then I have the graph force distance like this. I know that the work is equal to F times the displacement, so I can say that the area under this graph will give me the work done. Here the area is equal to the work done. As work done is equal to change in energy, so here I'm going to deposit elastic potential energy. So let's calculate it. So elastic potential energy is equal to the area, which is force times the amount of stretch over 2. As F is equal to K times X, let's put it here. So Kx times X over 2. I have the formula 1 over 2 Kx squared. This is the formula I'm going to use as deposited potential energy in elastic objects. I have a spring stretch 0.2 meter. By putting a 0.5 kilogram object in front, calculate the energy deposited in the spring. The formula is equal to 1 over 2 Kx squared. I'm going to put the values. The K is the spring constant given as 200. The amount of stretch is 0.2, so 0.2 square. So this is equal to 100 times 0.04, which is equal to 4 joules of energy. How many joules of work should be done on the spring to take its shape from first figure as in the second figure? We have the original length of the spring as 160 centimeters. So here the amount of stretch is equal to 20 centimeters, which is equal to 0.2 meter. And here the amount of stretch is equal to 40 centimeters, which is equal to 0.4 meter. The energy deposited here is equal to 1 over 2 Kx squared, 1 over 2 100 times 0.2 square, which is equal to 2 joules. And here the energy deposited is equal to, again from the formula, 1 over 2 100 times 0.4 square is equal to 8 joule. So the work done is equal to the change in energy. So change in energy is equal to the final energy minus the initial energy. The final energy is 8 joule. The initial energy is 2 joule. So the work done is equal to 6 joule. The identical X and Y springs, as they're identical, they have the same spring constants. They are in equilibrium, and we are going to find the elastic potential energies deposited in them. We are going to ignore the mass of the springs. When I examine the X, I see that it pulls only the K and L, so in total 3m mass. So for X, I'm going to use F is equal to K times X. So the total force applied to X is the weight of the 3m, which is equal to 3mg. So K times the amount of stretch of X. Let's look at Y. Y only is pulled by the mass 2m. So for Y, again from F is equal to K times X, the only force is equal to weight of the L, which is equal to 2mg, K times the amount of stretch of Y. So when you compare the amount of stretches, I can say that the X has a stretch of less 3 and Y has the amount of 2. So when I take the ratio of their energies, Ax is equal to 1 over 2 k times 3 square. Ey is equal to 1 over 2 k times 2 square. So they have the ratio 9 over 4. The given spring is squeezed by an amount of x and an object m is put in front. What's the ratio of the kinetic energy of the object at points K and L when the spring is released? When I squeeze it by an amount of x, the energy deposited in the spring as elastic potential energy is equal to 1 over 2 kx square. So when it comes to k, you see that the amount of stretch is increased to x over 2. So it has the deposited potential energy 1 over 2 k x over 2 square. So 1 over 2 k x square over 4. So you see that you have lost a 3-4 ratio of its energy. So if I say that this is equal to E, so at the beginning it has an energy equal to 4E. So where is the rest of the energy? The rest of the 3E energy is transferred to the object as kinetic energy. So if the spring comes to position L, so you see that here this is the equilibrium position. That means that there is no amount of stretch. If there is no amount of stretch, that means that there is no deposited potential energy. So all of the potential, elastic potential energy is transferred to the object. So at point L, the object will have all the energy of the spring, which is equal to 4E. So at position K, we have said that 3E goes to object, so it has the ratio equal to 3 over 4.